Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. In this module, we will learn the different disk scheduling algorithms. So, the learning objectives for this module are to understand the physical structure of secondary storage devices and to learn and evaluate disk scheduling algorithms. So, we have been learning about different file systems in the past few modules. So, when you are looking at a file system or the implementation of a file system, it comprises of three major parts. One is the user and the programmer interface to the file system, how the user or how the programmer can interface to the file system, issue commands to the file systems and so on. And then the next part is what is being implemented within the kernel or by the operating system. Those are the internal data structures and the algorithms that are used by the operating system for the implementation of the file system. And the third part is what resides in the disk. So, the structure of the secondary storage which accommodates the file systems. All these three parts put together form the different issues related to or the implementation issues related to a file system. And in this module, we will be focusing on the third part, that is the secondary storage structure and issues related to disk scheduling. So, first looking at the disk structure, as we all know, a disk provides the bulk of the secondary storage for the modern computer systems, and disk drives are addressed as large one dimensional arrays of logical blocks, where the logical block is the smallest unit of transfer, and this one dimensional array of logical blocks is mapped into the sectors of the disk sequentially. So, this first sector or sector 0 is the first sector of the first track on the outermost cylinder. So, when a mapping is being done from a file to this disk or the contents that are kept in the disk, you first look at this first sector and then go through the rest of the tracks in that cylinder and then go through the rest of the cylinders from the outermost to the innermost. So, likewise, logical address can be converted into a cylinder number, into a track number and to a sector number. So, when you are looking at a file will have logical numbers from 0 to some maximum, and those have to be mapped on to disk block addresses kept in the disk, and those will be mapped on to a cylinder number, track number and a sector number. So, this combination of cylinder number, track number and sector number will actually form the actual disk block address that is kept in the disk. So, now we will see this disk scheduling, why we need disk scheduling. So, when you have this disk, the operating system is responsible for using this disk in an efficient manner. So, when you are looking at a disk, it means that you need to have a fast access time and the disk bandwidth should be high. Whatever is being transferred should be as large as possible between the disk and the computer and the main memory. So, if you are looking at this access time from the disk, it has got two major components. One is the seek time. The seek time is the time for the disk to move the head to the cylinder containing the desired sector. The disk comprises of a number of cylinders and the head has to move on top of the appropriate cylinder before you try to read from any of the tracks in that particular cylinder. So, the time needed for the head to move to the cylinder is the seek time, and once the head is kept on the appropriate cylinder, then the disk has to be rotated so that the actual track is brought below the head. So, this is called rotational latency. So, the time needed for the disk to rotate the desired sector under the disk head is called rotational latency. So, what we need to do is that we need to minimize the seek time. So, whenever you try to access contents from the disk, the seek time should be as low as possible. The next parameter that we need to look at is the disk bandwidth. This disk bandwidth is nothing but the total number of bytes transferred divided by the total time between the first request for service and the completion of the last transfer. So, within a particular period of time, within the time when the transfer started and ended, how much amount of data is being transferred. So, this is called the disk bandwidth. So, the disk bandwidth should be as large as possible when you are trying to access data from a disk. And now we will see what happens during disk scheduling or why you need disk scheduling. Say when a process is needing I/O from the disk, or basically it wants to read from the disk, or if it needs to write to the disk. So, as a user, the programmer or the process will issue a system call to the operating system. The system call will have information, or it will tell information to the OS about whether the operation has to be a read operation or a write operation, that is whether it is an input or an output, and then it will have to give information about what is the disk address for the transfer. So, from which disk address it has to be transferred. It can also say what the logical address should be, and then what is the memory address for the transfer. It will have to say, suppose if you are trying to read from the disk, in the user space a buffer has to be provided into which information has to be read from the disk. Suppose if it is going to be a write operation to the disk, then the information to be written will be kept in a buffer in the user space, and from there it will have to be copied onto the disk. So, the memory address of these buffers into which you are trying to read or from which you are trying to write have to be specified, and then the number of bytes to be transferred also have to be specified. So, how many number of bytes you are trying to write to the disk or how many number of bytes you are trying to read from the disk, both have to be specified. So, if the desired disk drive and controller are available, then the request is serviced immediately. But if the drive or the controller is busy, then this request is placed in a queue of pending requests. So, because you have a number of processes that will be giving requests, say if there are 5 processes and all 5 processes need to read from the disk or write into the disk, then all these requests will be using the same disk drive, and therefore, it will be using the same disk controller. So, these requests from all these 5 processes have to be serviced by the disk controller, and it will be servicing it only one after the other. So, only if the disk controller is free currently and no other process is currently using the disk controller, then this process which is issuing a read or a write can get access to the disk, or the request of this read or write will be serviced immediately. If there are many other processes also waiting in addition to this requesting process, then this requesting process may have to wait. So, it will be placed in a queue of pending requests. Now, when one request is completed, the operating system will try to service the next pending request. Now, when it tries to service the next pending request, say there are a number of processes which have issued requests and all are waiting, and of all these pending requests, which should be serviced by the operating system first. So, how does the operating system make this choice? This is done by different ways in different algorithms, and these are called disk scheduling algorithms. So, the disk scheduling algorithms tell about how the disk is being scheduled among the different processes that are waiting to use the disk. So, now we will see different disk scheduling algorithms and the performance of each of the disk scheduling algorithms. So, there are several algorithms that are available to schedule the servicing of disk I/O requests, and suppose you have a request queue like this. Say you have requests for cylinders 98, 183, 37, 122, 14, etc., and so on. So, these numbers correspond to different cylinders of the disk. Totally, say there are 200 cylinders numbered from 0 to 199. Say currently the head is kept over cylinder number 53. Now, we need to look at different algorithms and see how each of those algorithms move the head to service these requests, and then we will see what will be the number of movements that are being made by the head for each of those algorithms and see how it is being minimized. Say if the number of movements of the head is more, then it means that the seek time is more. So, if the seek time is more, then the access time is more. So, here we are not looking at the rotational latency, we are only looking at the seek time, and these algorithms are focusing only to minimize the seek time. So, the first algorithm that we will see here is the first come first served algorithm. As the name says, whichever request arrives first will be serviced first. So, look at this diagram. This shows the movement of the head. Initially the head is kept at 53 and then there is a request for this cylinder 98. So, the head is moved from 53 to 98 and then from 98 it is moved on to the next request, that is 183, and then from 183 the head is again moved back to 37 because 37 is the next request, and then from 37 it is moved to 122 and then from there to 14 and then to 124 and then 65 and then 67. So, requests are serviced only in the order in which they arrive. But here you can see that, there is a request for 122, there is also a request for 124, but because this 14 arrived between this 122 and 124. So, after servicing 122 the process went on to service 114 and then again it moving back to 124. So, here you can see that this is a swing back and forth unnecessarily, and there you can see that the lot of swings that are happening back and forth unnecessarily. So, here you see that the head is moving a lot. So, the head is moving back and forth a lot. So, rather than doing this, if we say make the head move only for some amount of time, or say if the head is moving only close to the current head position, and if it is servicing all requests that are close to the current head position, then you can reduce the seek time. So, here in this the head movement is totally 640 cylinders, that is 53 to 98. You need to calculate it as 98 minus 53 plus 183 minus 98 plus 183 minus 37 and so on. So, if you add together it comes to around 640 cylinders. So, we try to move to another algorithm now, that is the shortest seek time first algorithm, where the head movements is reduced a little. So, in the shortest seek time first algorithm, the request is selected from the queue of pending requests based on the criterion that the minimum seek time will be the next service. So, if a service requires minimum seek time, that request will be serviced first. So, you choose the pending request which is close to the current head position, and this is also a form of this SJF scheduling, very similar to how we learnt shortest job first scheduling in CPU scheduling. There we try to assign a job which has got the shortest job, shortest burst time to the CPU. Very similarly, here you are assigning a job or you are trying to service a request which is close to the current head position. But the problem here is that it can result in starvation. So, we will see that with an example now here, the same example as we saw for FCFS. So, initially the current head position is 53. So, out of all these pending requests that are kept here 98, 183, 37 and so on, you try to choose the one which is closest to the current head position. So, to the current head position the closest one is 65. So, 65 is service, and then from there the next closest is 67 and the next closest is 37, etc. and so on. So, whichever request is closest to the current head position is serviced. So, here you can see that the head is not moving back and forth, it is not swinging back and forth, but it is only servicing requests that are close to the current head position. But the problem here is that it can result in starvation. Say at this particular time, say 37 is being serviced and this 98 has arrived much earlier than this 37, and after this 37 is being serviced, say there are many requests that are coming, fresh requests or new requests that are coming, which need to be serviced here in this position, say at around 15, 38, 49, 52, etc. and so on, then in that case all the requests here only will be serviced. The head will not be moved to this 98 unless it completes all the requests that have come in this particular region. So, what happens is that this request for 98 which had come earlier will be waiting for a long amount of time. Suppose if you are looking at this 183, 183 would have arrived much earlier compared to all the other requests, but this request for 183 will be waiting for a long amount of time because that position is not close to the current head position. But the advantage is that the total head movement can be reduced when compared to the earlier 640. Here the head movement is only 236 cylinders. So, the next algorithm, it tries to focus to reduce the head movement as well as try to reduce starvation. So, here what is done is that the disk arm starts at one end of the disk and it moves towards the other end, servicing all the requests until it gets to the other end of the disk. Once it reaches the other end of the disk, it will again move backward, move towards this other end, servicing all the requests while moving back. So, the head movement will be reversed and the servicing will continue, and this is very similar to this elevator moving up and down and servicing people. So, it is called the elevator algorithm. So, here you can see that the head movement is reduced to 208, we will see that in this example. So, look at this example. So, initially the head position is 53 and the head is moving towards one end, servicing all the requests. So, it services 37, then 14, and it also, but it still moves to the end of the disk till 0, and then again it moves backward. So, while moving backward, it will service 65, 67, 98, etc. and so on. So, while it moved here from 53 to 0, suppose if requests had arrived in the meantime between the 0 and 53, it will be servicing all these requests from 0 to 53, and only then it will service 65, 67, etc. and so on while moving back to the other end. So, here you can see that it will be servicing some requests here, and if more requests arrive at this point, then this 183 will be waiting for a longer amount of time, or the requests which are kept in the other end of the disk will have to wait for a longer amount of time. So, what is done is that they try to modify this algorithm to make the head move from say 53 to 0, and then while moving back it will not service any of the requests, it will move to the other end of the disk and then again return back and it will service in this direction. So, it will be servicing requests in only one direction. So, we will see how that algorithm works. So, this C-scan will provide a more uniform wait time than scan, and it will move, the head will move from one end of the disk to the other, servicing requests as it goes. When it reaches the other end, it will immediately return to the beginning of the disk without servicing any requests on the return trip. So, it will treat the cylinders very similar to how a circular list is, that will wrap around from the last cylinder to the first one. So, here you can see that this head is moving from 53 to 65, 67, etc. and so on, it goes on till 199. So, till 183 there were requests, but still it moves to this end of the disk 199, but in the reverse direction it does not service any request, and then from there it moves to 37 and service requests. So, we can see here that the circular scan does scanning from the current head position to one end of the disk, and in the reverse direction no servicing, then again in the same direction it will keep on servicing requests. So, here you can see that the average waiting time or the waiting time of the nodes that are waiting at the other end will be reduced. But the problem here is that you can see that from 193 the head moves till 199, but there are no requests here. there are requests only till 183, but still because it has to move to the other end of the disk, it just moves to the other end of the disk. Very similarly, when you are coming to this side, you can find that from 0 to 14 there are no requests, but still the head moves from 0 to 14 because it had moved from 199 to 0 and then it starts scanning. So, these movements are unnecessary. There is a movement from 0 to 14 as well as the movement from 183 to 199 are not necessary. So, what is done? They try to do a modified variant of this scan and C scan, and they call it as C look and look. So, this variant of C scan, the arm will go only as far as the last request in each direction and then will reverse the direction immediately. The arm does not go all the way to the other end of the disk. So, here you can see that in C look is just a variant of the C scan, but it goes to service only till this 183, and because there are no requests from 183 to 199, it does not move from 183 to 199. It just reverses the direction from 183 and goes back to 14 only. It does not move till 0, it goes only till 14, services 14 and turns back and starts servicing in the other direction. So, this is a variant of that C scan algorithm, that is, it does not move till the end of the disk. And now we will see how to select a disk scheduling algorithm. So, we have seen a number of disk scheduling algorithms and we will see which one is the best. So, here you can see that this shortest seek time first is the most common one, because it has a natural appeal, because it is increasing the performance, or it has a better performance compared to FCFS. And scan and C scan, they perform better when there is a heavy load on the disk. Say when there is a heavy load on the disk, SSTF will lead to starvation. So, when many requests keep coming, the SSTF algorithm will only service the requests that are close to the current head position. The requests that are far away from the current head position will not get serviced at all. So, it is better to move to this scan or C scan algorithm to reduce starvation. And the performance also depends on the number of requests and the types of the requests. So, that is what we see here. So, if the number is more, then the performance will vary for different algorithms. Suppose say you have only one outstanding request, then in that case all will behave like FCFS, but if the number gets increased, each algorithm will work in a different manner. And other thing is that, say, the request for disk service can also be influenced by the way in which files are allocated. We saw different file allocation methods in an earlier module, like contiguous allocation, linked allocation or indexed allocation. In contiguous allocation, the file is stored in contiguous disk blocks in the disk. In the case of linked allocation, the file will be stored in any one disk block, and from there will be a link to another disk block which can be kept in any cylinder, and from there will be a link to yet another disk block which in turn can be kept in any other cylinder, and so on. So, the disk blocks will be kept anywhere in the disk. Similarly, in indexed allocation also, the disk blocks can be kept in any place in the disk. So, they are scattered on the disk. So, if the disk blocks are kept contiguously, as in contiguous allocation, then in that case you need only limited head movement. So, you may not have to move the head at all if they are kept in the same cylinder, only you will have to rotate the disk to bring the corresponding track under the head. But in the case of linked or indexed allocation, the disk blocks are kept anywhere in the memory, they are scattered on the disk, and hence the head may have to move a lot. So, the way in which file allocation is done also influences the way in which requests are being made for disk service. And the next is the location of the directories and the index blocks. So, directories will have the entry about the name of the file. It will also have entry about the file control block, or say called as an inode in the case of Unix, and that will have information about the addresses of the disk block. So, when you are trying to open a file, you will have to first look into this directory entry and then get the file name, get the inode, get the addresses of the disk blocks, and then only you will get the contents of the file or the files data. So, if the directory entry is on the first cylinder and say if the files data are on the final cylinder, so first you will have to access the directory, that is you will have to access the first cylinder, and then to get the files contents you will have to access the final cylinder, which means that there is a lot of head movement that is involved. So, to reduce this, what can be done is that one thing that can be done is that is to go for caching directories and index blocks in main memory. So, that you when you are trying to access the directory contents, say you will have that present in the main memory, you do not have to go and access the disk. So, this will reduce the disk arms movement or the disk heads movement to a certain extent. So, this scheduling algorithm should be written as a separate module of the operating system, so that you can replace it with a different algorithm if necessary. So, this need not go as a part of the kernel of the operating system, the core of the operating system. It can be kept as a separate module which can be modified as and when needed. So, here we see that this SSTF or look is the reasonable choice for the default algorithm, because SSTF will service the request such that the head movement is very less, and look will service even when you are having heavy loads of services. So, the algorithms that we had seen till now, they are considering only the seek distances. So, the seek time only is looked at, because we are only looking at the head being moved from cylinder to cylinder. We are not bothered about the rotational latency. But for modern disk, this rotational latency can also be as large as the seek time. So, what is done is that the disk scheduling algorithms are implemented in the controller's hardware, which is built into the disk drive, and when the OS is sending requests, the controller will queue the requests and they will schedule them such that both the seek time and the rotational latency are improved. So, the summary for this class lecture is that we mainly focused on disk scheduling algorithms. First we saw this first come first serve scheduling algorithm, which services requests based on the order in which requests arrive, but this requires a lot of swinging of the head back and forth. And then we saw this shorter seek time first algorithm, which services requests which are close to the current head position, but the problem here is that it may result in starvation. The advantage is that there is less head movement. And then we saw the scan algorithm, where requests are serviced by moving the head from one end to the other end and then moving back towards the other end, then servicing the request. But the problem is that some requests may get serviced later, there is no uniform wait time. So, you go for this C-scan algorithm, where the requests go from where the request is serviced from the current head position to one end, and the reverse direction there is no service, and then again it moves back from that end position towards the beginning and services request. In look and see look algorithm, you do not go towards the end of the disk to service. Look and see look are variants of scan and see scan. Look and see look, they just service request only till when the requests are needed to be serviced, that is they do not move the head to the end of the disk, the head is moved only till the place where service is required. So, then we saw different performance comparison between the different algorithms. The references, thank you.